All right, I'm going to just keep doing some more examples. And these are going to get increasingly more complicated. But suppose we have this differential equation. I can just take the Laplace transform of both sides. So this becomes the Laplace transform of y prime plus Laplace transform of y. And the Laplace transform of e to the minus t is 1 over s plus 1. And this becomes minus y of 0 plus s times the Laplace transform of y plus Laplace transform of y is 1 over s plus 1. So notice, what did I do? I took the Laplace transform of everything, broke it apart, and I basically just expanded everything as far as possible. Once I've got everything expanded out, and by the way, this is going to be equal to 1, I now want to solve for the Laplace transform of y. So I can factor out an s plus 1, and I can add 1 to both sides, and now divide by 1 over s plus 1. And there's my Laplace transform of y. Now in this particular case, I can get y immediately because I can immediately look at this and say, the Laplace transform of t e to the minus t is 1 over s plus 1 squared. Okay. Yeah, why do I feel like there's a minus sign? And then the Laplace transform of e to the t is 1 over s plus 1. So that means y is going to be t e to the minus t, oops, that should be a minus t, plus e to the minus t. Again, this is just an algebra, and working with tables. And no constants of integration, so they just got that straight away. What if we had y double prime plus 9y equals 1? Y prime of 0 is 0, and y of 0 is 1. Now before we would have treated this as constant coefficient and gone through, find the characteristic equation, gotten complex roots, put together things to get the homogeneous solution and make a guess for the particular solution. Then I'd have two constants, and I'd have to use this to solve for the constants, and it would be a pretty awful mess. But now, I can just take the Laplace transforms of both sides. This is going to be minus y prime of 0 minus s y of 0 plus s squared times Laplace transform of y. I'm going to leave this term alone, and the Laplace transform of 1 is 1 over s. Okay, I've got everything expanded out. I want to solve for those two terms. I'm going to move those two terms over to the other side. So I'm going to have s squared plus 9 all times Laplace transform of y. Now this is 0, so I didn't leave that alone. This is 1, so I just add s to both sides. Now I get the Laplace transform of y is 1 over s times s squared plus 9 plus s over s squared plus 9. I like this one. This looks like Laplace transform of cosine 3t. And this one, not so much. So now I'm going to reduce this using partial fractions. So I'm going to have a over s, and then this is a second order degree polynomial, so I need a first degree polynomial on the top. So b times s plus c. So again, I am, just for the interest of brevity, I'm not going to go through and do this. You should be able to do this on your own by now. And you should figure out that a equals 1/9, b equals minus 1/9, and c is 0. So coming back to here, we get the Laplace transform of y is a over s, which is 1/9 times 1 over s, plus b, which is minus 1/9 s over s squared plus 9, and then the c is 0, so that's all we get. Oops, and I almost forgot. And I need... All right, we just dealt with this term. I got to bring this term down. So that's plus s over s squared plus 9. So the Laplace transform of 1 is 1 over s. Laplace transform of cosine 3t is s over s squared plus 9. So that means y is 1/9 plus a minus 1/9 cosine of 3t plus cosine of 3t, or, so 1 minus 1/9 is 8/9 cosine 3t. Okay, more examples. Y double prime plus 2y prime plus y is 0. Now in this example, if we had done this before, we would have gotten double roots and we'd have to do some weird stuff. We're going to see in this case some nice things are going to happen. We're going to basically just solve this directly. So if I take this Laplace transform of everything, get the Laplace transform of the second derivative plus 2 times Laplace transform of the first derivative plus Laplace transform of the function equal to Laplace transform of 0. Laplace transform of the second derivative is going to be minus y prime of 0 minus s y of 0 plus s squared times Laplace transform of y. I'm going to be a little careful here. This is 2 times Laplace transform of y, so that's going to be minus y of 0 plus s Laplace transform of y. I'm going to have plus Laplace transform of y, Laplace transform of 0 is 0. So y of 0 is 0, so that's 0, and that's 0, and that's 2. So I can add 2 to both sides. And in terms of the things, let me multiply this out because I want to be careful about that too. I'm going to add y prime of 0 to both sides, so add 2. So on the left, I'm going to have s squared times Laplace transform of y plus 2s times Laplace transform of y plus Laplace transform of y equals 2. Now I can factor out Laplace transform of y. So I get s squared plus 2s plus 1. There's Laplace transform of y is equal to 2. Divide everything by s squared plus 2s plus 1. And I immediately recognize that denominator I can write as s plus 1 squared. So y is going to be 2 times te to the minus t. Right, and you should recognize that the Laplace transform of t e to the minus t is 1 over s plus 1 squared. That's going to satisfy my initial conditions. So that's a quick check. Maybe it's okay. But notice I had a double root here. I didn't have to worry about different versions of e to the minus t. I just get this directly without any messing around. Okay, last example. This is going to be very similar, but the differential equation is just a little bit different. All right, so take the Laplace transform of everything. So my differential equation was y double prime plus y equals 0. Initial conditions, y of 0 is 0, y prime of 0 is 2. So that becomes the Laplace transform of y double prime plus Laplace transform of y prime plus the Laplace transform of y is equal to the Laplace transform of 0. This is minus y prime of 0 minus sy of 0 plus s squared Laplace transform of y. So I can deal with the Laplace transform of y double prime. No coefficients there, just 1, so I can be a little crazy. So that's going to be the Laplace transform of y prime is going to be minus y of 0 plus s times the Laplace transform of y. And then plus the Laplace transform of y. And the right-hand side is the Laplace transform of 0 is 0. Y of 0 is 0, so that term is 0. That term is 0, and y prime is 2. So I can add 2 to both sides. So on the left-hand side, I'm left with s squared Laplace transform of y plus s times the Laplace transform of y plus the Laplace transform of y equals 2. Can factor out a Laplace transform of y. I'm left with s squared plus s plus 1 times the Laplace transform of y is equal to 2. Then divide both sides by the quadratic. So I get Laplace transform of y is 2 over s squared plus s plus 1. And so now you should immediately recognize that I can't easily factor this, right? Because if I look at b squared is 1 minus 4ac. All right, so it's got complex roots, so I'm not going to mess with it. So I'm going to try to complete the squared. So let's see, I'm going to have s plus a squared is s squared plus 2as plus a squared. That means s equals 2as, so a is a half, and a squared is a fourth, so I'm going to add 1/4 and subtract a fourth from the denominator. So my Laplace transform of y is 2. I'm going to have s squared plus s plus a fourth. And then 1 minus a fourth is plus 3/4. So I get Laplace transform of y is 2 over the quantity s plus 1/2 squared plus 3/4. So in this case, my a squared is 3/4. So that's going to be square root of 3/4. So let me pull the 2 out. So this is going to look like sine, but to be sine, I need the square root of 3/4 there. But if I put that in the numerator, I have to divide by that. Otherwise, they're not equal. So notice those things cancel, though these two expressions are equal. So this becomes 2 times the square root of 4/3 times square root of 3/4 over s plus 1/2 squared plus 3/4. And that's 2 times the square root of 4/3. That's going to be the Laplace transform. So I'm scaling by minus a half. So I'm going to have e to the minus 1/2 t, and this can be cosine of square root of 3/4 t. Sorry, I did not leave enough room there. So that means y is 2 times the square root of 4/3 times e to the minus 1/2 t times cosine of the square root of 3/4 t. Again, you can leave it like that. There's no need to waste your time simplifying that. It's a perfectly fine expression.